input. And to give you an image of the system, I have here's a video. So it was developed only for Japanese. So
Yeah.
we copied. Software it takes
Do you import the picture or do you import
yeah, video. The picture movie. Just text. The picture is for human, not for us.
It would be also a goal to do it from a picture.
I prepare within the presentation. The file is huge.
You want me to give you the video?
So we copy and paste the text into the system and start parsing the sentences in the program. Parsing means the analysis of the syntactic structure of the sentences. You count the syntactic tree of the sentences in the program. In parallel to this analysis of syntax, the system derives the logical forms of the sentences and combine it into the logical representation of the program. And now the reasoning part is started. We put the logical form into higher dimension of the program and derive the answer with answer suite like this. In principle, readable, not very friendly that is readable. And in actuality, we have developed a few more systems for, say, Japanese, English, physics, and Japanese history and world history. We evaluated all these systems on a preparation test held by a private education company. The test is developed for preparation for a national standardized test for university admission in Japan. So the participant number of participants is around 400,000 or so. And our system was empowered human on several subjects like math, history, physics. And in total, these systems run here. The correction of AI systems with most of the human, average human, and it runs among top 20% of the participants. And the math solving systems were participated in another preparation test that was for University of Tokyo entrance admission. University of Tokyo is most prestigious university in Japan. And on its preparation test for math, the system achieved 10 out of 80 points on the literature course test. But on the science course test, it achieved 80 points out of 120 points. It amounts to 76.2 T-score. It means the system is ranked within top 0.5% of the most, I would say, best high school students in Japan. Today, in the language processing part of the math program solving system. And then talk a bit more about the system statistical modeling side of the system. This is a flowchart of the math program solving system. And it receives a program within text and with semantic dictionary including 8,004 forms, it translates the text into a logical form, as shown in the video. Then the logical form is further rewritten into a specific language, in this case, the language of real closed field. Then the quantifier elimination algorithm is applied onto the presentation and the answer is derived. That is the basic flow of the system. And the core of the language processing part of the system is a grammar, and its framework is called combinatory categorial grammar that was developed by Stephen and other engineers. And the main body of a grammar is lexicon. Lexicon is a collection of lexical items that is a triple of word and its category, syntactic category, and its semantic function. Here are a few examples of the lexical entries. The first one is for word circle, common word circle. So its syntactic category is N, and its semantic function is one phrase predicate circle X abstracted by X. And here, the verb includes has a category S backslash NP slash NP. That means it takes a noun phrase to its right and another noun phrase to its left and becomes a sentence. It means it is a transitive verb. And the semantic function of includes is shown here. It takes two arguments and they are in inclusion relation. That is the semantic function. And we can also write lexical entries for quantifiers like every or there exists A, B, and so on. And and these lexical entries combine into syntactic and semantic description of larger phrases using combinatory rules. Here are two examples of the combinatory rules. This rule says you can combine a phrase with syntactic category X and another phrase with category Y backslash X into a larger phrase having category Y with semantic function F applied to X. See? And another rule says you can combine these two phrases with function composition on the semantic function side, and its syntactic category is Z expecting Y to its left. With this kind of rules, you can derive, for instance, semantic description of a noun phrase, distance between P and Q. First, the entry for N conjunction and Q is combined with forward function application. So Q fills Y in this semantic function to derive this one. Then it is combined with P, and we have semantic function P, Q, pair of points. Then function distance is applied onto this pair and to derive this semantic function with syntactic category P. This is just for explanation. In actual sentence, the derivation tree looks like this is Japanese sentence, meaning let V be the cone formed by rotating the triangle and we see the x-axis where A is this point, B is this point, and O is this point. It's not very long sentence, but the syntactic tree is that huge. So I show close up this part here. It says X軸の周りに回転させて適応変数 in English. It roughly corresponds to a cone formed by rotating a triangle around x-axis. So writing a dictionary is the reverse process. I have a semantic description of a program or a sentence, and I decompose the meaning along with its syntactic form. That is the grammar development or lexicon writing. Here are some examples for a single word, area. It means immensity, it means area. For different usages of a single word, we need one lexical entry, a different lexical entry. For instance, for the usage like the area of triangle T1, we have this syntactic category and corresponding syntactic function. It has different category with the area S of triangle T, or T has area 1, or T does not have area greater than 1, and so on and so on. In the current dictionary, we have 32 lexical entries for this single one area. And in total, the current lexicon includes 55,000 lexical entries for 8,000 word forms. And grammar development is the most time-consuming part of the system development, but it's not the end of the story. With the grammar, we have to choose a most plausible interpretation of a given sentence. That is the problem of disambiguation. And the system sometimes produce very weird interpretation, as I will show shortly. So we have to have a mechanism to avoid such weird or strange interpretation. That is a problem somewhere between grammar development and disambiguation. That is the second problem. And further, we have to derive the logical form in a realistic amount of time. That is the algorithmic efficiency issue. That is the last problem. And all these three programs are handled with help of statistics. So I will explain how statistical modeling is used for these different kinds of processing issues. The first one is disambiguation. As you know, natural language is quite ambiguous in general, and it is also true on mathematical text. Here is a simple example of natural language ambiguity. He caught a cat on the tree. Here are two interpretations. One interpretation is that the catching a cat event happened on the tree. The second one is catching this cat on the tree, but the catcher maybe on ground, maybe on tree. It's unknown. So there are two different readings. For resolving this kind of ambiguity, we develop probabilistic models. Given a sentence, we quantify the probability for that sentence denoting this meaning or this meaning. And in actuality, these two interpretations correspond to different derivation trees for the same sentence. So we define a probability distribution on the space of derivation trees and use it for disambiguation. Schematically, it's like this. We have a space of sentence and interpretation. The grammar defines admissible region on this plane. It means we have basically we have only a finite number of interpretations for each sentence. So here is a limited region. On top of this region, we have a probability distribution like this. And given a sentence, we consider the intersection of this distribution on this line, and it gives the conditional distribution of an interpretation y given a sentence x. And we search for y that maximizes the probability on this distribution. That's the basic story. So far, so good. The grammar defines this region, and statistics defines a distribution on top of it. So it's a kind of cooperation between symbolic approach and statistical approach. That's okay, but the reality is a bit more dirty than this. I mean, the admissibility part of the interpretation is also modeled statistically. That means, in this view, every sentence allows arbitrary interpretation. But the interpretation not admissible in normal sense has a very low probability. I mean, suppose you say Mary likes chicken. We are going to interpret this. The basic interpretation is, of course, Mary likes chicken. It has very high probability like this. But it may mean Mary does not like chicken with very low probability. That is the statistical modeling of admissibility. Further, it may mean something that John Stewart knows with very low probability. That is the funny, but it's what happened inside the statistical model. This is the classical view I showed just before. The symbolic constraint defines a region, and the probability distribution comes on top of it. But in the second view, everything is statistical. Every sentence can have every interpretation, just with different. It actually happens in modern natural language processing systems like Google Translation. I will explain briefly about it now. In Google Translation, they map these words to a vector in a high dimension space like 300 dimension vector space. This mapping is run through a kind of supervised learning using translation patterns as the training data, or it can be run using just a bunch of raw sentences, that means word clustering. Either way, we have set up this mapping first. Then the translator looks like this. These blocks are vectors called hidden layer. The hidden layer here is determined by the mapping of this word to a vector and preceding hidden layer. Then this vector and the embedding of this word determines this vector, and so on and so on. And here comes the mark for the end of the input sentence. At this point, the system starts to select, say, French word that has closest distance to this vector, like you, and this output word is input to this step, and this vector is determined by this vector, and it again says another word, like, and it goes on until the last one, special one, is output. That is actually the mechanism working behind Google Translation. It's quite simple. So it does not know about syntax, it does not know anything about logic and so on. It just defines statistical or probabilistic distribution. And it's for translation between natural languages, but it also happens in the case of the interpretation of manifest. See this example. Let P be a point distinct from A on the line AB. It is not very fluent because it's a direct translation from Japanese sentence. A bit better way of saying it would be let P be a point distinct from A on the line AB. The correct interpretation is, of course, like this. P is on this line AB, but not at A. That is the first interpretation. But the system also outputs interpretation like this. P is a point distinct from A on the line AB. You see? The system says A is on line AB, and P is distinct from A. This part is quite, I'll say, funny, but anyway, system output it. And because it has no clue to choose between these two interpretations. The point is that point A on the line AB is, of course, wrong interpretation, but it is okay. It is perfectly grammatical. So the grammar cannot reject it. It's a matter of kind of pragmatics, like Gaussian maximum of B. See, this part tells nothing new about point A, so this interpretation should be wrong. So the situation now is like this. We have grammatical constraint like this, but inside it, actually we have more restricted association between sentences and interpretation determined by various principles of pragmatics. And this principle is not easy to formalize because it's like this, be real or be honest and so on. So it's quite hard to logically determine this constraint. So here comes the power of statistics. We collect a bunch of data and we hope the distribution somehow approximate the boundary here. That is another way of using statistics inside mathematical text interpretation. That's a dark story, but it actually happened.
Couldn't you do this also semantically, just by detecting that this is some sort of very simple statement or some tautology? Even like you could say that if something is a very, very trivial statement, then we probably don't want it, rather than doing it statistically. So we could use theorem proving to like if something has a very short proof or zero length proof because it's a tautology, then it could be another method how to prune such parses.
Not sure.
Okay.
It's really hard to see what is trivial.
Oh, you could look at the lengths of the proof.
Yes, talk about it.
Yeah.
And last one is process modeling. So far, we assume a probability distribution on top of space of interpretation Y. And so finding best Y among these Y with this distribution is a combinatorial optimization problem in general. And it is often very difficult to exactly find the maximizer of this distribution. And in practice, we can find exact solution only for a very simple probability distribution. That is the actual scale. So instead of scoring the probability of y like this, we can directly learn how to derive an interpretation. I mean, like this. This is a common way, one common way of modeling the process of parsing. We set up a queue here with the words in the input sentence, and we prepare a stack here. And any machine learning classifier like three-layer neural network receives input features from this data component and determines action like shift. So shift action means we could remove a word from queue to this stack. And this process of determining action and executing it repeats to some point. Like here, the classifier outputs this action we use with for function application. And we apply this action on top of two top elements in the stack. Like this. See? And it repeats until all the elements in the stack are combined into one. This representation is in one-to-one correspondence to the derivation tree. So it derives the derivation tree using a sequence of actions. The point is that modeling the sequence of action is much easier to formulate or learn a probabilistic distribution on the space of complex objects like logical form or derivation tree. So it is often done in a practical natural language systems. So it's more hard to interpret, but it's easier to define and learn. So the Google's translation system can be also seen in that regard. This part can be regarded as an automata outputting French word stochastically using the input vector here composed of this and this and these vectors. Here is simply an automata outputting words at each step. That is another way of seeing this. It is a kind of action one, action two, and so on. And now I'm going to conclude the talk on our mass sorting system was an amount of 0.5% of best Japanese high school students. We are very happy with that result. And I explained that the logic and the grammar are very important backbone of the system, but to make it work, we need some help from statistics to do these components. And here are some prospects, my personal prospects about the field of AI can improve. As you know, neural networks, especially deep neural networks, are getting more and more popular among all over the field. And it's also true in language processing and maybe in AI can improve. And the next important theme in coming 10 years will be the anatomy or reverse engineering of the learned neural network model. It's kind of interpretation of that model in terms of our asset logic or language. And as I talked in this presentation, different concepts developed in symbolic AI are crushed into a bunch of parameters like grammaticality, admissibility, plausibility, norm, and convention. These are quite different concepts, but they are uniformly represented with numerical parameters. So this mixture makes it's very difficult to analyze the parameters. And my hope is logic and self-improving provide some means to interpret the fragile data that I'm not sure currently how to do it. I do believe a very important research issue in current areas. That's all.
So I saw a lot about Montague graphs in the talk, right? So that's basically your approach. Did you also find a need to include the ideas of discourse representation theory to go beyond the sentence boundaries?
Right. So for the purpose of presentation, I just saw sentence representation. But the mechanism is a kind of discourse representation.
Okay.
So you already presented similar work during one of the previous AITP conferences. Have you done any work since then on this project?
For me, inside math problem solving or other.
I mean, what have you done since then?
Maybe the biggest progress is somehow related to his question. So far, we have developed a system analyzing a sentence, but we have to compose a cross sentence to derive a meaning of a program consisting of several sentences. That is one part. And another part is interpretation of math formulas in various disguises. That is another issue. And further development of grammar and so on.
I think the last time it didn't work from end to end.
Yeah.
So we had the last part, the second half of the system mainly for the simple computation. So from the formal the presentation of the problems to the answers, but this time the first half of the system was built in the last 2 years, and it worked from end to end.
Okay.
You mentioned neural network shift-reduced parsing and sequence-to-sequence models, but I was a little bit unclear about how those tools were integrated into your system.
No. I don't use sequence-to-sequence type system. It's just for experimentation. The actual parser used in our system is more like the transition-based parser.
It's a shift-reduce
Yeah.
neural network parsing. Is the logical form part of that parsing process?
Currently, yes. We can postpone the composition of logical part later. We can first derive syntactic tree and then use it to derive the logical form.
I guess the question is, so in a typical shift-reduce neural network parser, features are computed that feed into the neural network.
I see.
Do those features involve logical? Do you have logical form?
No, currently no.
The design of exam questions or whole exams is a difficult task in itself. So does the, let's say, Japanese exam committee use your tool to grade questions, to check whether they are unambiguous, or to compare last year's exam to this year's exam?
I hope so, but not really. But actually, the checking of test programs or bug in the test program is quite a problematic issue in Japan. We found a few incidents involving test bug last year.
How sensitive is this system to the style of questions that appear on these exams? And can you apply to different various
I see. Of course, it depends to some extent the style of the test. The system is basically for read-writing style test. So the basic types of questions are to prove something or to find a quantity like length of this segment and so on.
Yeah, but for example, not every math problem can be reduced to real field.
Yeah, close. Yeah, right. But the language of RCL covers approximately 40 to 60% of the programs in the university entrance examination.
Makes sense to speak again.